Right now, somewhere in Virginia, there's a building that draws as much electricity as a small city, just to run chatbots a few seconds faster. That's not an exaggeration. That's the actual state of American computing in 2026. And while that building keeps expanding, a handful of engineers in Germany, Australia, and the United States have already built something that quietly makes half of that building unnecessary. A working computer chip that performs calculations no ordinary processor can touch. It needs no refrigeration, no clean room, and no data center at all. It fits in a server rack. It runs on a normal wall outlet. And some versions of it are already sitting inside a US government laboratory today. This is not a concept. This is not a 5-year roadmap. This is happening right now, and almost nobody outside the industry has noticed. To understand why this matters, you first need to understand just how strange the current situation actually is. Artificial intelligence has an appetite problem. According to the International Energy Agency, global data center electricity demand crossed roughly 485 terawatt hours in 2025, a jump of about 50% in AI-specific facilities alone. Gartner's own numbers, published in June 2026, show worldwide data center power demand climbing past 130 gigawatts this year, on its way toward 290 gigawatts by 2030. In the United States specifically, researchers at Lawrence Berkeley National Laboratory project that data centers could consume somewhere between 6, 7, and 12% of the entire country's electricity by 2028. Some newer AI server racks now draw as much power as 65 households combined in a single rack. States like Virginia and Georgia have started passing laws forcing data center operators to help pay for the electrical grid upgrades their own buildings are making necessary. And it isn't just electricity. Every one of those data centers needs water for cooling, land for construction, and a place on the power grid that utility companies now have to plan years in advance. In Ireland, data centers already account for roughly a fifth of the entire country's electricity use, and forecasts suggest that could climb close to a third by 2026. In parts of the United States, getting approval to connect a new data center to the grid has become one of the biggest bottlenecks in the entire AI industry. Of the roughly 12 gigawatts of new data center capacity announced in the US for 2026, only about a third was actually under active construction because the power simply wasn't ready yet. So here's the uncomfortable question. Nobody in Silicon Valley likes to answer directly. What happens when the compute we want keeps growing faster than the power grid can keep up? For years, the industry's answer has been build more data centers, build more power plants, build more transmission lines. But there's a second answer that almost nobody was talking about publicly until very recently. And it doesn't come from building bigger. It comes from building differently, using a completely different kind of physics. And that's where this story gets genuinely strange. Quantum computers were supposed to be the ultimate energy hogs. If you've ever seen a photo of one, that gold chandelier-looking structure hanging inside a glass cylinder, that's not decoration. That's a dilution refrigerator. And it exists because most quantum chips, including the ones built by IBM and Google, rely on superconducting circuits that only work when cooled to a fraction of a degree above absolute zero, colder than deep space. A single one of those refrigerators can cost anywhere from a few $100,000 to more than $2 million. The helium-3 gas some of them use to reach those temperatures is a byproduct of nuclear material decay, and it can cost more than $2,000 per liter. Add in the vibration isolation, the specialized shielding, and a team of cryogenic engineers earning well into 6 figures. And you start to understand why a single enterprise quantum system from a company like IBM is estimated to cost more than $10 million just to acquire before you've even turned it on. And the refrigerator is only half the burden. Once a quantum chip is cold enough to work, engineers still have to run hundreds of individual wires down into that near absolute zero chamber to control and read out every single qubit without letting any outside heat leak in along the way. That wiring problem alone is one of the main reasons scaling these systems up to thousands or millions of qubits has proven so difficult. It's a bit like trying to build a taller and taller skyscraper while every single pipe, wire, and cable still has to be threaded down through the same narrow shaft at the center. At some point, the shaft itself becomes the limit, no matter how strong the building is. For a decade, this was treated as an unavoidable cost of admission. If you wanted quantum computing, you accepted the refrigerator. You accepted the warehouse-sized facility. You accepted that this technology would live inside a handful of national labs and tech giants, forever separated from the ordinary server rack down the hall. But a small number of teams quietly decided that assumption was wrong. And what they built instead is the part of this story most people haven't heard yet. The breakthrough didn't come from making a better refrigerator. It came from asking a completely different question. What if you built your qubits, the basic unit of quantum information, out of a material that's already naturally stable at room temperature? The answer several teams landed on was diamond. Not the metaphor, actual diamond, engineered at the atomic level. Here's the simplest way to picture it. A regular superconducting qubit is like trying to balance a spinning top on a moving table. The slightest vibration or heat knocks it over, so you have to freeze the whole room to keep it steady. A diamond-based qubit is more like carving a tiny groove directly into solid rock. The material itself is so rigid, so pure, that there simply isn't enough thermal energy at room temperature to shake it loose. Engineers do this by removing a carbon atom from a diamond's crystal lattice and replacing it with a nitrogen atom, creating what's called a nitrogen-vacancy center, a tiny, naturally occurring quantum system sitting inside the diamond that stays coherent without any cooling at all. Think of the difference this way. A superconducting qubit is a bit like trying to keep a house of cards standing on a table in a room full of people walking around. You have to empty the room, seal the windows, and remove every gust of wind just to keep it from collapsing. A diamond nitrogen vacancy qubit is closer to carving a tiny notch into a boulder. People can walk around it, the room can stay at normal temperature, and the notch simply doesn't move because the material around it is naturally rigid enough to protect it. An Australian company called Quantum Brilliance, spun out of the Australian National University in 2019, has spent years building exactly this. And here's the part that connects it directly to an American audience. In 2025, Quantum Brilliance deployed a small cluster of its diamond-based quantum processing units at Oak Ridge National Laboratory in Tennessee, one of the U.S. Department of Energy's flagship research facilities. The system, nicknamed Qual, sat inside a rack that looked almost identical to any other server in the building. No dilution refrigerator, no vacuum chamber, no separate climate-controlled wing. According to the lab's own account, the goal wasn't to replace supercomputers. It was to test whether small, room-temperature quantum processors could work alongside classical computing hardware as a kind of specialized coprocessor, the way a graphics card works alongside a regular CPU today. And Quantum Brilliance isn't alone. In mid-2026, a German startup called Saxon Q, building on more than 2 decades of diamond research out of Leipzig University, unveiled 2 commercial processors, one with 128 qubits, another with 512, claiming to be the first diamond nitrogen vacancy systems to move meaningfully past the 10-qubit mark. According to the company, these systems run on ordinary AC power, require no cryogenic cooling whatsoever, and use somewhere between 6 and 10 times less energy than equivalent GPU computing clusters. That last number is the company's own claim, not an independently audited figure, so it's worth holding with some healthy skepticism. But even a fraction of that efficiency gain, if it holds up under outside testing, would be a meaningful shift. But diamond isn't the only path researchers are taking to escape the refrigerator. And the next development is happening on the other side of the world, which raises questions of its own. In China, a spin-off from the Chinese Academy of Sciences called Zhongqi Wuliang unveiled something called Qinghe No, one at the World Artificial Intelligence Conference in Shanghai in the summer of 2026, a neutral atom quantum computer, a different physical approach entirely that also skips cryogenic cooling and slides into a standard server rack. A related lab, Zhongke Kuyuan, had already delivered an earlier system called Hanyuan-1 to a China mobile subsidiary in October 2025, a 100-qubit machine that fit inside 3 equipment racks, reportedly reaching gate fidelities above 99% on single-qubit operations. By May 2026, a follow-up version, Hanyuan-2, had shrunk that down further into a dual-core cabinet design using less than 7 kilowatts of total power, not much more than a couple of household ovens running at once. To picture a neutral atom system, imagine using lasers instead of magnets to hold individual atoms perfectly still in midair, like tiny beads suspended in a grid of invisible tweezers, and then using those suspended atoms themselves as the qubits. Because the atoms are floating in a near vacuum rather than locked into a superconducting circuit, this approach also sidesteps the need for extreme cold, even though it still needs careful control of lasers and vacuum conditions. Now here's where honesty matters more than excitement. No independent peer-reviewed benchmarks have been published for most of these Chinese systems yet. The performance numbers so far come primarily from the companies themselves and from conference demonstrations, not third-party verification. Experts in the field differ sharply on how close any of this, American, European, or Chinese, actually is to solving problems a classical computer can't already handle. Diamond-based systems like Quantum Brilliance's are currently working with a relatively small number of usable qubits, and the company itself has said publicly that a system it considers commercially useful, in the range of 60 to 100 qubits doing meaningful work, is more likely several years away, not something available today. In other words, room temperature operation is real and increasingly well documented. Better than a supercomputer at real-world tasks is not something any of these systems have proven yet. And some researchers argue that jump could still take a long time to arrive, if it arrives at all in this generation of hardware. So why does any of this matter if the machines aren't beating supercomputers yet? Because the thing that's actually changing isn't raw computing power. its geography. Think about what a data center really represents. It's not just servers. It's an entire ecosystem built around one core requirement. Keep everything centralized because the infrastructure to run it is too big, too power hungry, and too fragile to put anywhere else. That's why your data has to travel from your phone across the country into a warehouse in Iowa or Virginia, get processed, and travel all the way back. Adding delay, adding energy cost, and adding a single point of failure every step of the way. A room temperature quantum chip breaks that requirement. If a quantum processor can sit in a normal rack on normal power, it doesn't have to live in a warehouse anymore. It can live in a hospital, doing molecular simulations for drug discovery on site. It can live on a factory floor, optimizing a production line in real time. It could eventually sit inside equipment far from any major grid connection, doing sensing and computation without needing a data pipeline back to a central facility at all. Picture a hospital in a mid-sized American city that wants to run molecular simulations to speed up drug discovery, but can't justify flying samples and data back and forth to a cloud quantum service hundreds of miles away, let alone building its own cryogenic facility. A room temperature quantum accelerator sitting in the same server closet as its regular IT equipment changes that math entirely. Picture a logistics company trying to optimize delivery routes across a fluctuating supply chain in real time, or a materials science lab trying to design a better battery chemistry without waiting weeks for cloud queue time. None of these use cases require a system that beats every supercomputer on Earth. They require a system that's simply present, reliable, and affordable enough to sit where the problem actually is. That's the part that actually changes the equation. Not quantum computers get faster, but quantum computers stop needing to live somewhere else. And for a country like the United States, currently racing to build enough electrical capacity just to keep its existing AI ambitions alive, a computing approach that sidesteps the power problem entirely is not a minor engineering footnote. It's a genuine strategic advantage, if the technology matures the way its developers are hoping. It also explains why a facility like Oak Ridge National Laboratory, a lab that has historically handled some of the country's most sensitive computing research, was willing to be among the first in the world to bring one of these room temperature systems in-house, rather than waiting for the technology to fully mature somewhere else first. Before you get too far ahead of yourself, picturing quantum laptops next year, it's worth being clear-eyed about the limits. These are still what researchers call NISQ-era devices, noisy, intermediate-scale quantum systems. They are not fault-tolerant. They can't yet run the kind of large-scale, error-corrected algorithms that would let them crack modern encryption or simulate a truly complex molecule end-to-end. Superconducting systems from companies like IBM and Google, despite needing all that cryogenic infrastructure, currently operate at far higher qubit counts and, in certain narrow demonstrations, have shown results classical computers genuinely struggle to reproduce. Meanwhile, a third camp of researchers is betting on yet another approach entirely. Photonic quantum computing, which uses particles of light instead of trapped atoms or diamond defects, pursued by companies working on silicon photonics for both computing and secure quantum communication. Each of these approaches, superconducting, diamond, neutral atom, and photonic, solves a different piece of the puzzle, and none of them has definitively won yet. The race between cold and powerful versus room temperature and portable is nowhere near decided. Some engineers believe the room temperature approach will always trail behind in raw qubit count, simply because packing enough atomic scale defects or trapped atoms into a chip without cooling gets physically harder as the numbers climb. Others believe that portability itself will eventually matter more than raw power, the same way a smartphone eventually mattered more than a mainframe, even though the mainframe was more powerful on paper. Nobody knows for certain yet which bet wins, and it's entirely possible the honest answer is that both approaches survive, serving different jobs. One style of quantum computer bolted to a national lab doing the heaviest research problems, and another style scattered across hospitals, factories, and field equipment doing lighter, specialized work no classical chip can match. There's also a national security dimension worth naming plainly, because it's part of why this technology is being watched so closely in Washington. Quantum computing has long been treated as a strategic asset, not just a commercial one, because sufficiently advanced quantum machines could eventually threaten the encryption methods that protect everything from banking systems to military communications. A version of that technology that no longer requires a massive, easily identifiable, cryogenically cooled facility is, by definition, a version that becomes much harder to track, count, and regulate. That doesn't mean any of the systems built so far pose that kind of threat today. The qubit counts are still far too low, and the error rates still far too high for anything close to breaking modern encryption. But it's part of why governments in the US, Europe, and China are all funding this kind of research simultaneously, rather than leaving it entirely to the free market. What we do know is this: The assumption that quantum computing requires a specialized, refrigerated, multi-million-dollar facility is no longer universally true. That assumption has quietly cracked open in the space of about 18 months across 3 different countries, using at least 2 different physical approaches. And the first real-world deployment of one of these systems is already sitting inside a US Department of Energy laboratory, not in a press release, but in an actual building, running actual tests right now. If you've made it this far, you're clearly the kind of person who wants to understand where technology is actually heading, rather than just the headlines. So if that's you, hitting subscribe means you won't miss where this story goes next, because this is genuinely one of the fastest moving corners of science happening today. Here's the honest way to think about all of this. We spent the last decade being told that the future of computing was about building bigger models, bigger data centers, bigger power plants to feed them. What's happening with room temperature quantum chips suggests a quieter, less dramatic possibility that some of the most important progress won't come from scaling up at all. It'll come from figuring out how to shrink the infrastructure around the intelligence itself, so that computing power stops being something you have to travel to and starts being something that simply exists wherever you happen to need it. Whether that unfolds over the next 3 years or the next 15, the direction is now unmistakable. And it's worth watching closely, because the companies and countries that solve this first won't just have faster computers, they'll have computing that nobody else can easily catch up to. If this kind of deep, honest look into where technology is really headed is something you want more of, consider subscribing so you don't miss the next one.